Morning, folks. How's lab 2? I see some grumpy. So you got waveforms on the VGA? Yes? This is ish, yeah. Anybody got, anybody still having trouble with Busmaster? Any questions you'd like to ask about writing Busmasters? Yeah, I did a clarification this morning on Piazza of really related to what Mohammed talked about on Friday, and that is you can test your entire VGA write state machine by simulation. You don't need to have it hooked to the VGA because all it is doing is responding to the output of the EBAB, which consists of a bus ACK. And you're generating addresses, you're generating data. The addresses represent the XY position, which you can parse in the test bench back into X and Y. If you do that, and then you plot Y, you should get a waveform back out. Is that what you ended up doing? Yeah. So the address you generate is some 32-bit monster with the lower 10 bits being X, the next 9 bits being Y, and you could parse out the Y and look at it in the test bench. And I wouldn't bother putting this on the FPGA until you can reconstruct, take the address that your VGA state machine, or your VGA state machine is producing, and parse it back into X and Y. Because everything else, putting it on hardware is very slow. That's what Mohammed was talking about on Friday. And all you have to do to generate the ACK in the test bench is to detect when the code is when the device under test is asking for a bus write and assert the ACK, because there is no bus delay in the test bench. So a fairly simple test bench will do the whole test right up to the EBAB. The EBAB is presumably correct since it's supplied by the university program. So you should be able to bolt the buses together and it should work. So any questions on this? There's only 3 days left on this. Now is the time for questions. How many people have spent over 1,000 hours on this so far? No, but realistically, how many people have spent over 20 hours trying to get the bus master going? Okay, so no question on bus masters. None, really? It's all working for everybody? So the next piece of this is the HPS, the high performance system, has to be able to control the solver. One thing, I was reminded on the weekend that probably when you do a screen erase from your state machine, it's leaving a little band of crud at the bottom of noise or something. You can erase the whole screen by writing a black rectangle from the HPS. You do a VGA box with the size of the screen as the parameter, and it erases the whole screen. So that's what you want to do when you press start. I think the Lab 2 requirement is that when you start the simulation, it starts with an erased screen, and when you say pause, it just halts. So when you press start on the HPS, the first thing it does is erase the screen, and then assert the control line for the solver state machine to produce 32 solution points, or however many you've decided to map to one point on the screen. Any problems adding parallel I/O ports to the HPS? Anybody done it? You all had some obscurity as yet undetermined, right? Well, I'm going to be in lab Wednesday afternoon. And of course, there's office hours tonight at 4:30 to 6:30. Tomorrow night, 4:30 to 6:30. But you're expected to demo this Thursday night. And so this is really your last chance to ask questions in a group format. Of course, there's always Piazza, except students aren't using that, with one or two exceptions. I'll be happy to do an example again if you want. But if nobody says anything, we'll go on to lab 3. So on Wednesday, let me just peer at my what passes for my brain these days. On Wednesday, which is the 1st of March, I got nothing after 5760 all afternoon. Given that it's one day before deadline, shall we just skip lecture and go directly to the lab at noon? Okay, we'll do that for Wednesday. Guys, don't be shy. I don't believe that most people have this lab working yet. Demo, you want to see more code? You want an explanation of code? Don't know what to ask. Yeah, there is that. There's a couple of approaches. One is, if all you're seeing on the screen is a smear, you could slow down your state machine to 5 points per second, reset the system, and see if it's drawing points. So you could slow the system down. There's no reason it has to run at 50 megahertz. You could run it at 5 hertz. And it'll solve just the same way. You might consider that, where you can, if you slow it way, way down, you can look at the state transition matrix on the LEDs, for instance. Now, some states are going to be pretty tedious. If you decide to erase the whole screen, it's going to go through 600,000 states before it gets out of that loop. So you don't want to slow that down. But if you're determined to put it on actual hardware, you might want to slow down the execution. Otherwise, simulate. Simulate until you have the whole VGA state machine completely running. You can even, so the top level module, you have to generate the bus ACK. Oh yes, you also have to completely test. You have to generate H-sync and V-sync pulses. That's easy. You can look those up, but they almost don't. It doesn't matter what the detailed timing is, as long as the H-sync's shorter than the V-sync, and there's about 480 of them per V-sync. So you could generate these three signals and completely test the synchronization of your state machine with the VGA monitor driver. Well, shall we dive into the wave equation, both feet? So for lab 3, I'm going to ask you to solve the two-dimensional wave equation. I thought I'd write it out because I suspect that most of you haven't thought about this in a few years. But as always, there's the wave equation associates a time derivative with a space derivative. And in this case, the time derivative we're going to be looking at is the acceleration of one point on the membrane. So this is, if we have this grid of points, and we look at one point, what we're going to be looking at is the acceleration perpendicular to the grid. And that's going to be related to the forces, which are given by partial of u with respect to x squared. This is really what this says is, in the x direction, what's the difference in stretch between this spring and this spring? That's what that's saying. That's the net force in the x direction, plus the second partial of u with respect to y squared, which is the net force in the y direction, the difference of differences of the endpoints. And we're going to add in a little bit of numerical damping here. We're going to say that there's going to be some damping coefficient which is proportional to the first derivative of time. That is to say, it's proportional to speed. So there's some sort of viscous damping. This thing, the drum is in air, so the air is damping the vibration. The C term, speed of sound, the speed of the wave, is going to be abstracted away a little bit. It's going to be, as we convert this into a computational form, because computers don't do real well with continuous derivatives. You have to discretize. You have to make this differential equation into a difference equation so that you can solve it. So the next step is to try and figure out what the appropriate differences are for each of these terms. So if we convert this into difference form, one of the lowest order ways you can represent the difference of differences is to say we're going to have, oh, we need a notation here. All right, so u of I, j, n. So I is the x coordinate, j is the y coordinate, and n is time. So we could say that an approximation of the second partial of u with respect to t is un plus 1 ij minus un ij minus, so that's a first derivative in time, because we're stepping one step forward. And we're going to take the difference of differences, so then we have a un ij minus un minus 1 ij all over delta t times delta t, so it's delta t squared. And a little inspection will show that that's easily written as n plus 1 ij minus 2 un ij plus un minus 1 ij over delta t squared. And we can do the same thing for the space derivatives. So, but in this case, the space derivatives are all going to be taken at the same time. So we're going to have now that the first space derivative, dux squared, d squared u by dx squared, is going to be u, you know, maybe I better put the screen up. Oh, I can put the board up. Okay. Let's do that for right now. So we're going to write then the second partial with respect to x as u I plus 1j minus 2 times u n ij plus u of n I minus 1 j over delta x squared plus u n I j plus 1 minus 2 u n I j plus u n I comma j minus 1 over delta y squared. And for simplicity, a little bit later, we're going to set delta x equal to delta y and just make it a delta d. Plus, minus eta times du dt. We have to be a little careful of this because one thing we can notice about these terms is that they are balanced around ij. They're balanced around ijn, which means they're second order correct. And we want the first derivative term to be second order correct. And so we're going to make the approximation of the first derivative un plus 1 ij minus un minus 1 ij. So those samples are centered around, if this is the n plus 1, and this is the nth, and this is the n minus 1 sample, then at least we're taking a derivative that looks like that. It's the average of those two slopes. But that means that we have to bring this over to delta t. So this is what we're going to solve. And what we need to solve for, we know all of the positions at time n equals 0. We assume that we know all of the positions at time n minus 1. or 0 minus 1 at time minus 1, which is really the same as saying we know the position and the velocity. So we need two sets of initial conditions, and what we're going to do is to solve for n plus 1 time ij n plus 1, which we do not know, based upon the n's, the n minus 1 time, and n minus 1 time here. So I could bore you to tears with the algebra. How far up does this go? Doesn't go any higher than that. So do I have to actually raise this manually? How? You never know what you're going to find when you raise one of these things. When I was teaching in 101, I used to put all the boards up and down before class, so I knew what was on all of them before the class came in. Because sometimes you got surprised. So, if we rearrange this monster, and let's just turn it off. First of all, we're gonna define a parameter rho, which is a measure of velocity given by c times delta t over delta x quantity squared. This is kind of a normalized speed. It's a fraction. It's a speed given in fractions of the grid size, really. So it's dimensionless. And delta x here, it's inferred that delta x is exactly the same as delta y, so we don't have to worry about which direction the wave is propagating in. And there is an interesting condition called the Courant condition, which says that for any stable solution, this ratio has to be strictly less than 0.5, which basically says the wave can't travel faster than half a grid step per time step. If we do that, then we can solve for u n plus 1 I j, which will be the shape of the drum head at time t equals n plus 1, assuming we know its position initially. You are going to know its position initially because you're going to set it. And what you will probably do is either give it an initial velocity, so you strike a drum head. What are you doing? Setting the position or the velocity? Both. But you're going to give it some initial position, for instance, and some velocity, which could be 0. But this can't be just one point that you're hitting like this. So you cannot just give it an impulse function. Why? Because it's an impulse on a grid and it's guaranteed to alias. So you have to give it a distribution of energies. It does not have to be Gaussian, but it does have to be relatively smooth. So one possibility is to give it a distribution of energy that looks like that. It's not quite smooth. It has first order discontinuities here, which generates a little bit of harmonic activity, but not much. So you might give a strike with a center position, 1 grid away, 2 grids away, 3 grids away, 1 grid, 2 grids, 3 grids in both x and y. But you know n. So when all the factoring is done, need 3 levels of brackets here. We got 1 plus eta delta t over 2 to the minus 1, which looks like a divide but isn't. Big bracket times rho times square bracket times uni plus 1 comma j plus u at time n I minus 1 comma j plus u at n I j minus 1 plus u n I comma j plus 1 minus 4 u n I j which this has been factored, but this is really what we're calculating here is the average of the differences of the 4 springs that attach this mass to the masses on each side of it. Plus 2 unij minus 1 minus eta delta t over 2 times u n minus 1 ij. That's the velocity component. End of curly brackets. So this gives a formula for advancing the solution 1 time step. And you say, oh man, that's a mess. And you're right. But in terms of arithmetic, it's not really very bad, because you're looking at 4 adds, a subtract, a multiply by 2, shift left, a multiply by 4, shift left twice. And so the only real multiplies are by this reciprocal, this term, and by rho. To make it more interesting, where did I put this? Ah, yes. I'm going to make rho dependent upon the amplitude. In other words, it's going to be nonlinear. It's a nonlinear drum, which is much more realistic. And so rho is going to be given by, now I'll save that detail for later. I'll save that detail. Now, how can we simplify this a little bit? Well, so the first thing to note is that but I left out something here. Wait a minute. Yeah, okay. So the first thing to notice is you can simplify this slightly, because if you're really doing a drum, if you're really making a drum, then you would expect the damping to be rather small. Otherwise, you don't get a boom sound, you get a click. So drums have a fairly high Q. They have a fairly low dissipation. So eta is small, which means this term, eta delta t, is small with respect to 1. Which means that 1 plus eta delta t over 2 to the minus 1 is very adequately Taylor expanded. Remember Taylor expansions? Taylor expanded into 1 minus eta delta t over 2. And if you were careful about how you chose eta, remember, I'm not telling you what eta to use. You can use any eta you want. If you chose eta carefully, then eta delta t over 2 could be a power of 2. And so you could reduce this multiply to an add and a shift. So what you're going to do, what this whole lab is how fast can you calculate this equation for as many points as possible, for as big a I, comma, j array as you possibly can. Consistent with getting a new value for each point at 48,000 kHz, which is the audio sample frequency. So you're going to try and optimize the solution to this. And I think if you add it up, let's see, it's 1, 2, 3, 4, 5, 6 adds, plus a couple of one multiplied by row because it's going to be nonlinear. And so it's going to be something like 10 operations total with all the shifts. So you should be able to make a fairly small state machine that does this calculation. And then the question is, how many copies of this state machine can you put on the FPGA? And there's all kinds of detail there. There's all kinds of trade-offs. For instance, you could make a fairly heavy state machine that uses a RAM block for intermediate memory. In other words, it's like a little CPU that only knows 3 instructions: add, shift, left, and multiply. You're going to make a little CPU or a little state machine which uses a RAM block to maybe do 1 row of the drum, or maybe 1/4 of it. We'll talk more about this. What I do not have a good feel yet for is how fast you can solve this with the HPSs. You can use the HPS to solve this. High performance systems should be good for around 200 million floating fixed point operations per second per processor. So you figure 200 million, that's 2 times 10 to the 8th divided by 10 operations per node per time step times 50 times 10 to the 3rd hertz. And what do we get? We get Let's see, we take out 4 of these and we put that a 4 there. So we have 10,000 divided by 50, which is 1,000 divided by 5. That's only 200 nodes. So using both HPSs, you can get about 400 nodes, which is the minimum requirement for this lab. Not coincidentally. So my guess is that whipping up a C program and solving it on the HPS might be useful as a first step in understanding the problem, but is not going to get you all the way there. You're going to have to build parallel hardware. What seems to be a reasonably good approximation, or at least to my ear sounds good, and I took a few liberties with the exact solution. You can look up, the search terms would be tension-dependent velocity on a drum head, if you're into this. But what I found worked is that setting rho effective as equal to the minimum of 0.49. This made sure it never went to 5.5. 0.49 times some rho 0. That's the unstretched rho. That's the low amplitude rho. Rho 0 plus some middle point, let's say ij, some uij in the middle of the drum. So I equals j equals middle index times some tension gain, some tension gain squared. So this is a small effect at low amplitudes, but becomes much more dominant at higher amplitudes. Because rho effective is now a function of uij, the system is nonlinear. And that also means that this multiply has to be a real multiply, uses a real multiplier, and not just a shift in scale. So any questions about this?
So I've kind of forgotten. To make the audio, are we just going to pick a random point and sample that for the...
Well, yeah, not quite a random point, but one point. Yeah, I would say the middle of the drum or close to the middle of the drum.
Okay.
Someplace. Since you're sampling this one anyway, you might use the same one. And you're going to be using the audio codec abstraction, the module, the QSYS module, which abstracts away the audio codec into a FIFO. So you're going to be loading a FIFO with samples. Because of the way the audio codec works, you have to load both the left and right samples into the FIFO separately. Although I don't expect you to have a stereo drum. That could be cool, but don't expect it. So we're taking the grid. We're taking a fairly large grid. Bigger the better. solving it so that the time at t equals 0 is propagated to t equals 1. The shape of the drum at t equals 1 is propagated to t equals 2, and so on. This is a boundary value problem and an initial value problem. What would be reasonable boundary conditions for a drum? What would be reasonable boundary conditions? The edge of a drum is stretched on a frame, right? Usually. Not all drums, most drums. Which guarantees that to a first approximation at the boundary ui b jb equals 0. So the edges of this drum, the edges of the compute region that you're going to be solving are going to be clamped at 0 and will never be updated.
You get to count those as nodes.
Excuse me?
You get to count those as nodes.
Sure. The drum has to be approximately square, by the way. This disallows the solution, which is awfully easy to solve. So the drum has to be approximately square. So for a free plate, let's say that you have just you got a steel plate hanging from a string and you whack it with a hammer. What are the boundary conditions for that? Oh, I can see the wheels turning. There's no forces on the edge of the plate, right? Because it's free. It takes, to bend a plate requires force. Therefore, the plate cannot be bent because there's no force on the edge, right? Therefore, the partial of ui with respect to x must be 0. And the partial of uj with respect to y must be 0 on the boundaries. How do you enforce that? I said, okay, I can set these all to 0. Bing, done. How do I make this boundary condition? I want to ensure that there's no slope on the edge of the drum, because if there were, there'd be a force there. Well, all right, whatever this node is, I'll just copy it to the edge. Done! No slope. So you would calculate these nodes, you'd copy it to the edge, you'd calculate again all of the nodes, copy it to the edge. I'm not asking you to do this, but you could do it if you want to make something that sounds more like a gong and less like a drum head. My MATLAB code, you can actually tune from fixed boundary to free boundary smoothly. The initial value, so these are the boundary values you have to choose. You also have to choose an initial value, which we talked about before. I would suggest, let's say that so what you're going to specify is u of I j at t equals 0 and u of I j at a fake time minus 1 time step. So let's say we make this look like this, yoink, and let's say we make u minus 1 look like that. Why is that a bad idea? Remember, you're going to be doing this. You'll probably do it in fixed point. So you have to worry about overflows. What is the effective velocity? It was 0. Now it's this huge deflection. This sucker must have been moving like that between those two times. Therefore, there's a huge initial velocity in addition to the initial position. If they add up to make a next time step that's greater than 1, you overflow. So a very conservative thing to do is to make the boundary conditions for n, 0 and minus 1 be the same, which means that there's no velocity. You're starting this thing as if you pluck the center of the drum up, held it, bink, and let go. So, part of the specification of this lab is 3 different sounds. You could change the width of this distribution. The narrower the distribution, the higher the pitch of the resulting oscillation corresponding to higher modes of the drum. And it's the difference between hitting with a big mallet on a drum head and hitting with a very narrow stick. You'll get a higher distribution of more distribution of higher frequencies with a narrower stick. You could change the boundary conditions. You could change row 0. You could change row 0, which will change the pitch. Lower row means lower velocity, longer wavelength, lower pitch. You could change eta, which will change the damping, giving you either a slower decaying sound or a faster decaying sound. So you get to choose what combination of 3 things you decide to implement, with the one exception that one of them must show an audible nonlinearity. There must be at least one of the examples that shows an audible nonlinearity. Any questions? This is a big chunk. It's all math. We'll start talking next time about implementation, how to parallelize this. But that will be Friday, because Wednesday we're going to go directly to lab. How early do you want to be there on Wednesday morning? Or is that late Tuesday night? I hope not. I do not condone working all night on projects. It's a bad idea, psychologically and performance-wise. We do need to talk a little bit about generation statement. Wherever you talk about stamping down lots of copies of code, it sure would be nice if you didn't have to do that by hand, because it's error-prone. And there is Verilog has a meta statement called generate that allows Verilog code to generate Verilog code. In any case, you're going to simulate the hell out of this before you build it, because it takes forever to build these things with hundreds of units. Maybe an hour to compile. You don't want to do that very many times. All right, so you must simulate up to the point of running the audio state machine and loading the FIFO, right, before you put it on silicon. Okay.